So now we know the relationship between potential energy and work, right? This is their definition of their change of potential energy. Their change of potential energy is equal to negative of the work done. Right? So this is our relationship between these two quantities. But we also know that what work is equal to negative the initial integral from the initial position to the final position of the force. In this case, I'm going to write it specifically as the x component of the force, since that's the portion parallel to the displacement, times then my differential distance at which it is going to integrate. Now, from this, since this says that my integral of my force is equal to my change of potential energy, then that means there has to be some sort of relationship then between the force itself and also the potential energy. So let's think about how that would actually work. So in this case, what I'm going to do is take both of these and divide by delta x. So that means my left-hand side then is going to be equal to delta u divided by delta x, that is equal to minus 1 over delta x integral from x initial to x final of the x component of the force integrated over the displacement. Now, from here, then what I'm going to do is take the limit of both sides as delta x then goes to 0. Now, remember that according to calculus, the limit, in this case, of delta u divided by delta x, and the limit that delta x goes to 0 is simply equal to a derivative. This then is going to be the derivative of u with respect to x, then is equal to minus 1 over the derivative, or actually the derivative with respect to x, then my integral of x initial to x final, the x component of the force integrated over the displacements. Now, for the right-hand side here, what we know is that what? If I integrate over x and then I take the derivative with respect to x, all that does then is actually cancel out the integral. So in this case, the derivative here is going to cancel out my integral, which means that this then is going to be simply equal to negative of the x component of the force. So what this basically tells me then is that my x component of my force then is equal to negative the derivative of the potential with respect to position, or in terms of vectors, this is then going to be the x component of the force and then in the I hat direction. So what does this mean? What this means then is if I move in the x direction and I have a change of potential energy going from one x position to another x position, so meaning that what? If, for example, now it's here, so this is my position, this is my potential, and let's say I initially start off here at x initial, and then I end over here at x final, and then I have a change of potential going from one position to another position. It does something like this. Then what this means then is I had to have a force. Okay? That's what this thing is telling me. So what it's telling me then is that the force that it experienced then is equal to simply the slope of the tangent line that connects the two of these. Okay? So this is then the magnitude of the force in the x direction, which then is equal to the derivative at that particular point. Now, the negative sign actually tells me the direction of the force. What this says then is that the direction of the force then is equal to opposite to the direction of the slope, which basically means that what? In this case, since my slope is positive, that means my force has to be negative, which means my force would be pushing back in this direction. So this is then the relationship in one dimension, but in 3 dimensions, so in 3D, this thing then says that my force is equal to minus what's called the gradients of the potential. So in terms of derivatives, this is equal to minus the partial derivative of the potential with respect to x in the I hat direction, minus the partial derivative of the potential with respect to y in the j hat direction, minus the partial derivative of the potential with respect to z in the k hat direction. So this may look kind of scary, but all partials simply mean is that it's a regular derivative, but it's only a derivative in one direction. So what that means is, for example, this first term is saying how the potential changes as x varies or x changes while keeping both y and z constant. Right? Where the second term says the same thing. So this is seeing how the potential changes as y changes while holding x and z constant, and etc. So all you're imagining is that you're moving in the y direction and you're seeing how this potential here changes going only in the y direction. So this is the actual formal definition of the relationship between the two. But going back to this picture, basically all it means is, again, if I have a change of potential energy going from one point to another point, then there had to be a force. right? And then the direction of that force is then just opposite to the direction of the change of potential, which means that it's just looking at the opposite of the direction of the slope. So again, if my slope is positive, that means my force is in the negative direction. But if my slope is negative, that means my force is in the positive direction. So another way to kind of think about this is to think about a slide. So let's say here's my slide. Here's the ladder going up to the slide. And then I try to take a bowling ball. So if I take a bowling ball and then I try to roll it up the slide by giving it initial velocity, then this thing is going to follow the contour of the slide, where the contour of the slide would simply be equal to the potential. And then as it moves up, in this case, we know it has to slow down, which means that the acceleration is going to be in the opposite direction in which it is that it's traveling, which means, again, if I'm looking at this in terms of slopes, right, each one of these then has a positive slope, which means the acceleration is in the opposite direction. So it's a nice kind of analogy you kind of think of, again, trying to roll this bowling ball up the slide. So this is then my relationship then between the force and the potential. Now, what I'm going to be mostly interested in this for is to look at things that are called potential versus position plots. Now, let's look at kind of an example of this. So here is my, say, vertical axis, which is going to be the potential, and then my horizontal axis, which will represent the position. And let's say that my potential does something like this. Something kind of like that. Take that guy out like that. Beautiful. There we go. So good. So what is happening here? So what we're going to imagine is that what? We have no non-conservative forces. So what does this mean? So this means that the work done by the non-conservative force is equal to 0, which means that what? My change in mechanical energy must be equal to 0. So all this means then is that my initial mechanical energy must be equal to my final mechanical energy. Okay? Which means that overall, my mechanical energy is simply going to be equal to a constant. Okay? So what this means then is I'm going to have some sort of constant energy. So let's say this is my value of constant energy. Something like this. Okay. Now, what is some information I can actually get out of this plot? Well, the first thing I can get out of this plot is since my mechanical energy is equal to a constant, and mechanical energy is simply equal to the kinetic plus potential energy, is equal to my total mechanical energy. What this thing says then is that what? My kinetic energy at any point then is going to be equal to my mechanical energy minus my potential energy. So this means that what? As long as I know the total energy, which is what my red line is here, and I know the potential energy, which is my blue line, then I can establish exactly what the velocity is at any given point. Okay? So what does this mean? So this means if I had a particle here, slowly moving or initially moving to the left with some velocity v, what's going to happen is what? As it's moving to the left, the potential energy then is going to be decreasing as it moves to the left, which means that according to this, my kinetic energy has to be increasing. So as it goes down, my kinetic energy in this case then would have to be rising. Right? So I'm getting an increase in kinetic energy until it starts going back up, where my kinetic energy is going to decrease until this position, and then it's going to keep moving down. So in this case, my kinetic energy is going to increase again. So in this section here, it's going to decrease. And then once it gets over here, it's going to decrease until eventually it reaches this point here. So what happens at this point then is that my kinetic energy has to go to 0, which means that in this case, my total energy is simply equal to my potential energy. This point here is what we call the turning point. So my turning point is when my object is going to momentarily stop, meaning that the kinetic energy will go to 0, and then it's going to turn around and then go all the way back out to wherever it is that it began, since there's no non-conservative forces in this case. So turning point is simply when that, again, my total energy is equal to my potential energy. Right. So all this thing says then is that what? I can find then the location of the turning points. So for example, if I had my total energy was actually equal to, let me use a different color, let's say the purple line here. So in this case, I would have two turning points. I'd have one turning point here and then one turning point here. Right? So in this case, I can then establish exactly where all the turning points are based off of the total energy. I can also then establish exactly what the total kinetic energy it has at any given point by knowing simply the total energy and the potential energy. What else can I find? Well, I can also find the force, right? We know the force now is simply equal to minus the derivative of the potential with respect to position. So what that means then, again, if I was looking at a given point, so let's say this was the point of interest, I would then draw my tangent line. So in this case, then the magnitude of my force would simply equal to the derivative of the potential at that point, i.e. the slope of the tangent line, and then the direction of the force would be in the opposite direction of the slope, which means in this case, I would have a negative slope. So in this case, my force would be pushing in this direction, which again makes sense because as my particle is moving up, the potential has to slow down, which means my acceleration is in the opposite direction. And then when it's rolling down, it's speeding up, which means the force has to be in the same direction. So this is another thing I can find. So this plot also allows me to be able to find all the locations or the force at any location. Another thing it allows me to do, that color, is look at these positions here. Right? So these positions are what we call stable equilibrium. So what's a stable equilibrium? So imagine that you have a bowl and you have that bowl upright and you put a marble inside the bowl and you drop the marble. What's going to happen? Well, the marble is simply going to oscillate back and forth around the bottom of this guy, where this point here is the equilibrium position. Which basically means that what? If I put my particle at the equilibrium position, it's not going to do anything. But then if I move it from one side to the other side, it's then always going to go back to its equilibrium position. So that's what we call stable equilibrium. So it always wants to go back to equilibrium. Great. Now, since it wants to go back to equilibrium, what that means then is it creates the stable equilibrium position. Right? Now notice at the equilibrium position itself, the slope of my tangent line at the equilibrium position is simply equal to 0, right? Which means that my derivative at this point is equal to 0, which means that it has 0 force. Okay. So at stable equilibrium, this guy simply has 0 force. Now I can also identify positions such as this one here, which is what's called an unstable equilibrium. So this is unstable because, for example, again, if I took my same bowl, but now I flip it upside down. So in this case, when I put my marble on top of the bowl and I blow on it, it's got to roll away and never come back. So this one goes away, never coming back. But it's an equilibrium position because, again, if I look at the derivative, or I look at the slope of my tangent line here, again, in this case, I know the derivative of my tangent line is simply equal to 0, which means, again, I have 0 force. So for a stable and unstable equilibria, I have 0 force on each one. However, they're different in their concavity. So let's talk about that. So in this case, what I know is that what? For a stable equilibrium versus an unstable equilibrium, both of these guys simply have that the derivative of the potential at that point is equal to 0, which means that they have 0 force. However, the stable equilibrium has that its concavity is up, which means that's what? The second derivative at the equilibrium position is positive, while for the unstable equilibrium, the second derivative of the potential with respect to position evaluated at the equilibrium position is negative, right? So this is what we call concave up. This is what we call concave down. Or you can think about this guy as being what? A local minimum. And then this guy is what we call a local maximum. So buried inside of these wonderful plots here is a ton of information. So again, as I'm giving you the potential, and then I tell you specifics about the particle, that will then establish the total energy. So from there, what we can find then is what? Again, going back to here, what is the kinetic energy at any point? Where are my turning points? What is the force at any given point? And where are all of my equilibrium positions? I can then find all my stable and unstable equilibrium positions. So inside of these guys, again, is a ton of information buried inside of it. And our job then is to basically pull out all this information by finding the locations of equilibria, which ones are stable, which ones are unstable by looking at the concavity, being able to determine if it's going to make it to a point or if it's going to run into a turning point based off of the total energy. And then if it's going to run into a turning point, where's the location of the turning point? What is the force at the turning point? And then also, if it does make it, then what is going to be the force along the path, or if it has enough energy to get past a point, then what is going to be the velocity by the time it gets there, and what's the force it's going to experience as it gets there. So things like this. So here, we're going to be working on examples of this in class. We'll be doing that on Monday when you guys actually return. And then from there, we'll finish off this chapter by going back to power and then talk about the relationship, or what power actually is, I should say, not the relationship. So again, these are what the relationship then between the force and the potential energy. We're going to use that mostly to talk about these potential versus position plots, which again have all of this beautiful information buried inside of it. We just have to massage it out. So I'll leave it here. The rest of this we'll keep working on Monday. And yeah, I'll see you guys on Monday.